Okay, hi, and welcome everyone to the pitch event of our Deloitte Quantum Climate Challenge 2022. Live. Yeah. Yeah, thanks. So we are live from Berlin, and well, my name is Barbara, and in real life I'm the lead of Deloitte's Quantum.Link, but today I'm here on stage as your host, so I will guide you through the afternoon. Okay, so this is actually the first installment of our Quantum Climate Challenge. That is why it's called Quantum Climate Challenge 2022, but we are planning on doing this on a regular basis now in the years to come. So spoiler alert, next year there will be a Deloitte Quantum Climate Challenge 2023. And if you want to participate, suggest a topic, become part of our jury, or anything else, please come forward, because we highly believe in ecosystem and crowd innovation and, well, innovating together. And this is also why we teamed up with KI Park for this year's event. And we would, welcome you all to participate with us next year. Okay, so what is this Quantum Climate Challenge format all about? Why do we want to do this now on a regular basis? Well, first of all, we want to foster innovation, and we also want to raise awareness about quantum technologies and the way this can be used to tackle climate-relevant problems. And within this overarching aim, this year our challenge focuses on aviation. So as you probably all know, the emissions from combustion engines of planes have a very large negative impact on the climate, and especially given the massive amounts of air travel that is going on each year. And so in this challenge, we asked our participants to find solutions that can help reduce the negative impact of flying via flight route optimization with quantum computers. So specifically, we asked them to develop a quantum algorithm or a hybrid quantum classical algorithm or a quantum-inspired algorithm. So I assume that everybody who is here today visited our website at least once and knows a bit about the setup, but just in case anybody is tuning in who doesn't know the setup yet, here's a quick recap of what happened so far. We published our challenge task together with some real data on an online innovation platform in early March, and then the participants had around 6 weeks' time to work on their solutions. And overall, we had 130 registered team on the website with people from 20 different countries from 5 continents. Unfortunately, nobody from Australia. So if you're listening in from Australia, next year, please help me raise my KPI of continents participating from 5 to 6. Yeah. But today, we will hear the top 5 teams that our jury selected present their solutions and answer any questions that you might have about their work. And why do the teams do this? What is in it for them? So the first place team will get, of course, fame and honor, but also 5,000 euros. And then the second place team will get 4,000 euros. Third place team, 3,000 euros. And then for the fourth and fifth prize, 1,000 euros each. And in addition, we have prizes from Terra Quantum and from Anacor is how it's pronounced, I'm very sorry, for the first 3 places. Okay, and here you can see what will happen today. So before we dive into the pitches, we have another highlight for you. So Karen from Terra Quantum will give a keynote speech, and I'm very happy that he's here and that he agreed to talk to us today. And then we will have the pitches with breaks in between, and during the pitches, each team has 20 minutes to present their solutions, and this is followed by 10 minutes of question and answers each. And straight after the pitches, the jury will sit together and discuss the solutions and the pitches and select the winning teams. So while the jury puts their heads together, you all have the chance to meet the finalists a bit closer off stage. So all the finalists have tables over there, And you can go there, meet them, network, and, well, ask the questions you didn't dare to ask during the official Q&A. And I'm sure they are all happy to answer everything you want to know. And then once the jury has reached a verdict, the winners will be announced here on stage again, and this will happen at around 5:45, so 5:45. And after that, it is time to start networking. I was about to say drinking, but I guess I should say networking. That sounds more professional. OK, so now I already mentioned the jury quite a lot. So let's meet the ladies and gentlemen who have the very difficult task to choose the most promising solutions today. Unfortunately, not all of them could make it to Berlin, but we have 4 out of 8 with us here in the front row. And then we have, I know, 3 of them at least currently listening and watching very closely online. And we have 1 more member in the process of arriving. So hopefully he will be here before the first pitch starts. OK, but I will start with the introductions with the jury members that are here. And I will start with Andrea Lübke. She is Senior Vice President, Corporate Strategy of MTU Aero Engines. Very happy that you're here. Thanks for coming. Thanks for being part of that. And then we have Anton Kaya. He is a software engineer of Lufthansa Systems and responsible for the flight navigation systems and leader. Yes. Are you? Yes. Yes, that is what my team told me at last. And we have Oliver Hasse with us. He is the head of real-time simulation of DFS, that is the German Flight Safety Authority, and he's also a lecturer of aircraft design at the Technical University of Munich. Yes. And Jan-Rainer Lahmann. He is an IBM Distinguished Engineer for Quantum, and he's also a member of the IBM Academy of Technology. Okay. And so moving on to the jury members that are with us virtually, we have Sabina Jeschke. Please also give an applause for her. She is a professor for information science and mechanical engineering of the RWTH Aachen. She's the CEO of KI Park, senior advisor of Deloitte, and she's also the co-founder of her own quantum startup, Quantagonia. And then we have 2 members or actually we have 3 members of the German Aerospace Center, so Volker Greve, he is the one who is in the process of arriving. So if you see somebody sneak in and then move to the first row, that's him. And we also have Sigrun Mattes and Patrick Jöckel from the German Aerospace Center. They are all staff of the Institute of Atmospheric Physics. And all of them already won numerous prizes for aviation awards and the advancement in scientific computation. OK. So actually, so when we chose this overarching topic for our quantum challenges, there was no long discussions. We actually really quickly agreed that we wanted our challenges to tackle climate-relevant issues. And obviously, as you all know, climate change affects us all, and every contribution counts towards a more sustainable future. And I'm very happy that we at Quantum.Link are not the only ones to think that quantum technologies should be leveraged to tackle climate-relevant problems. So I'm really very happy that Karen agreed to give a keynote speech here today. You can already start moving to the stage. So he wrote a really exciting and great white paper about use cases of quantum for sustainability. So he's an absolute expert in this field. And I know that this is also a topic that is very close to his heart. So please give a big round of applause to Karen, our keynote speaker. For you.
Thank you, Barbara. Thank you to Deloitte for organizing this. I think this is so cool. I'm so glad we have a quantum computing challenge for climate change in 2022. Thank you to Ollie and Marcus as well for making this happen, and I'm really happy to be here. And it's really, right now, it's a really exciting time in the quantum space. Earlier on in the week, I was at The Economist, commercializing quantum event in London, and you could really see the energy, from people outside quantum about quantum. And that was so exciting to see. So today, the plan is as follows, right? I'm going to build it up. I'm going to tell you a little bit about myself, about Terra Quantum, about QMware. I'm going to talk about climate and quantum and the intersection between these two. And then we're going to emerge from that and talk about what we need to happen about this intersection to make things real, to make impact actually happen. So a little bit about myself. I really like innovating. I like doing stuff with disruptive technology that makes things useful. And I've done this across the board, be it butlers in London, to vapes, to overcome smoking, all the way to art, to even working as a race car design assemblage engineer at RoboRace, where we worked on zero-emission vehicles for Formula E, to even building a platform to connect captured carbon dioxide from direct air capture sites to users in industry. I've also worked at a number of firms like Accenture, Sear Partners, and my own company, ADIS, which looks at how we can bring together connected thought. One thing that I want to say is that, we all have really unique experiences in our life, and these great, unique experiences and things that we have lead to ideas that come from unexpected places. I myself have spent a lot of my time in theater, in dance, and the creative aspect of things is very important. We don't only need the mathematicians, the physicists of today. We need them, yes, but we also need people who are a bit creative, who have a little bit of a rebel insight in them to make things happen. And some really cool things that I've done, like climb really high mountains, go through adventure, and build things that matter. Now, I'm part of Terra Quantum. I'm head of growth and product there. And Terra Quantum is a quantum services company. We truly innovate by making quantum technology accessible. We have a quantum as a service business across algorithms, compute, and safety. In algorithms, we offer hybrid quantum algorithms for optimization, machine learning, and simulation. In compute, we have our own hybrid quantum cloud called QMware, which is easily accessible and provides advantage for application-specific use cases today. We also have a safety division, which looks at post-quantum cryptography, long-range secure communications, and a ton of other cool stuff from the safety domain. We recently raised one of the largest Series A quantum funding rounds in Europe with 75 million plus, and are backed by investors like Lakestar. We offer an end-to-end native full quantum stack. Just some examples of things that we're doing across industries. We made our work very recently with Volkswagen Public. Okay, there we worked with them on workflow scheduling. Optimization is how can you maximize the use of existing tools and resources in assembly lines. And we work across sectors. So, we're working in healthcare to financial services, and there's lots of applications that hybrid quantum technologies can impact that we are working on. Now, today, I want to give you this key message. This intersection between quantum and climate really matters. And aside from my work in quantum with Terra Quantum, I also have a community called Entangle, which is powered by the Quantum Insider, where we foster a community to make or give a space for people to come and talk about this intersection. We've actually written a really good white paper on it, which I'm happy to share afterwards. Yeah. So I wanted to bring to life some applications that are directly linked to sustainability powered by quantum technologies that we are working on today, just to make you feel how real this actually is. With Uniper, we're working on predicting carbon dioxide and NOx emissions more accurately in power plants to help inform the way they change these settings, the control settings of how the power plant actually works. Here, in this case, it's a biomass power plant. We're also working with them on LNG shipping logistics, which is how can they, this is a problem today, how can they get their ships very efficiently across different ports across the world in the most cost-efficient and clean way from a marine perspective. We're also working in the logistics space on quantum-powered route planning. Here, specifically, we work on reducing empty miles. Empty miles are miles that are driven by trucks without any load on them. About 30% of the miles to bring any good or product to you comes from a truck, okay? And it is driven empty. Empty miles are waste, and getting rid of empty miles will help us greatly in reducing emissions in the transport sector. This is another project that we're working on with a customer of ours in the retail and grocer space. So just completing this build-up section, right, I wanted to show you this amazing video of Robert McNamara. He's a surfer, okay, and about 10 years ago, he went to this place called Nazaré in Portugal, okay, and he saw these big, massive waves, okay? Nobody went and surfed these waves before he got there, okay? And this guy was like, you know what? I really want to surf these waves. I want to feel the adrenaline. So my question to you today is, are you someone like the people standing there who wants to watch these waves? It's fine. You know, you can watch disruptive, great tech come and watch it take over industries. Or are you someone who wants to actually ride the wave? You know, you might fall down sometimes. You might ride a great wave. But, you know, who are you? So today, we're going to say we are going to ride the wave, right? We're not going to be spectators. And that's why all of you are here today, is to ride that wave successfully, not just fall off. But if you fall off, there's a lot of combinatorial fodder that is advantageous to other people as well. OK, so now I'm going to get to the climate after the build-up. In my opinion, just 3 numbers that matter when we talk about the climate problem. The first number you probably are all aware of is the 2 degrees Celsius number that we need to be within the bounds of. But there's 2 other numbers that are not very publicized, okay? 565 is the amount of gigatons that we can release and stay within this 2 degrees Celsius limit. But the last number, that's the problem. 2795 gigatons. That's the amount that we are going to release if we continue on our path that we are on today. Can you see the discrepancy between the two? That's the problem, okay? So we need to stop this from happening, because if this happens, there's no way we're keeping to the 2 degrees Celsius limit. If you were to think about the climate crisis, the problem is really unique, okay? It's not as simple as saying, let's just solve one small part and it will help. The problem is systemic in a way that you need to understand the second, the third, the fourth order consequences of you making a change and improvement in the system. The timing matters. It is urgent. Doing something now will probably take a long time to be realized. And when it is realized, that is when the impact is actually felt. There's a lot of good pressure from the government, and carbon price is increasing, which is good for us all. But there's a lot of greenwashing out there. And greenwashing is something we want to be hyper aware of in a way of how do we measure the impact of a quantum tech-powered climate solution? How do we make sure that it's legitimate? How do we make sure that it's actually helping rather than taking us backwards? And that's a question that is very open-ended, and we actually are doing some work with GESDA and other big quantum tech players to see how we can measure this better through an open quantum climate initiative. Now, the problem, many people say, is not actually clear, but it is, okay? It's very clear. You know, we need to change the way we make things, the way we plug in, the way we grow things, the way we get around, the way we live. And it's not like we don't have sustainable solutions to do this today. We do. Okay? We have solutions that do one of the three things. They either stop you from emitting, they reduce the emissions you have, or they help you capture the emissions and reuse them or store them underground. It's either one of these three things. It's as simple as that. All the solutions you have out there have one of these three things. The important thing to remember is that it's not just one solution, but it's many solutions that are part of the overall picture. Now, I want to talk about quantum now that we've gone to climate. It was purposely that I went to climate first, because you might have expected me to go tech first with quantum, right? So it's always about the problem, the application, and then the technology. So quantum is everywhere. It's not like quantum is here, quantum is now. Quantum is everywhere, right? It's made possible the phones you hold in your hands. It's in the light that is making me seeable. It's everywhere, yeah? And quantum is actually so different, it's special. We can't think about it the same way. It's not like just making a candlelight more brighter, faster, more accurate. No, it's a move to a light bulb. We need to understand, moving from fire to put it on and off to moving to an adjuster to put this light bulb. It's a completely different mechanism. And the way to think about this paradigm shift is the same way you could think about what happened after we were able to compute. When we had a machine to compute, it changed things. When we had a machine to connect us, it changed things. What's happening right now is we're creating a shift that will change the way we do so many things. Those things are what you guys are actually imagining and thinking about today. One thing I want to say is that it's not just only about compute. Everybody talks about compute and algorithms. Quantum is so much more than that. It's about the way we communicate. It's the way we secure. It's the way we image things. So the quantum information science spectrum is large, and the applications span not just compute. Now, there's a problem that exists with true native quantum processors today. They're not good enough. We know that. They're not commercially viable. And there's this clear divide that exists, a battle between classical technology on a software and hardware level and quantum technology, and a clear divide that exists between quantum software and quantum hardware. And we at Terra Quantum, we've thought long and hard about how could we actually solve this. And this is why we have a hybrid quantum computing approach. We complete the donut. And for every application that we build, we have hybrid pipelines that use the best of quantum and classical together to enhance performance on an application level. And we make this hybrid happen not just through hybrid quantum algorithms, but also through our hybrid quantum cloud and our research to push past Moore's law with ferroelectric negative-based capacitance chips. There's a great white paper we've released recently as well, which highlights how we make practical application-specific advantage possible. Now, this is not just theory. This is accessible today, and we're actually offering a prize to the winner where they will get 48 hours of time on our QMY machine, which makes them execute these hybrid quantum algorithms on our hybrid quantum cloud, benchmark them, and see how they can productionize quantum for an end user. Now, just to summarize, the way quantum is going, it's hybrid. It's increasing in performance. You can get more out of the systems today. It's incredibly modular. There's lots of collaboration ongoing in the ecosystem. Accessibility is increasing, and cost is decreasing rapidly. Now, where does this leave us? Where does it leave us when quantum and climate collide? Now, we thought about this deeply, and we saw 6 key pillars where quantum would have a role to play in climate mitigation. And just some examples to give you, all the way from modernizing cold chains in pharmaceuticals to cellulose-based products, there's lots of opportunities. It is wrong to say there's not enough applications for us to go after. However, for us to win, we need to make quantum commercially attractive. And what's very important is that the premiums that you have to pay to use quantum need to be financially attractive. Now, there's a great metric that Bill Gates uses called the green premium, okay, where they measure what is the additional cost someone needs to pay for a more sustainable solution. And only when this more sustainable solution is economically more competitive is that when it wins. So we thought about this, and we said, OK, what if we think of it about this from a quantum perspective? Which are the industries where we can not only deliver a performance enhancement, but more importantly, we can ensure that this performance enhancement is scalable and adoptable. And the only time it's adoptable is when it is commercially attractive from a point of view that you create enough value that that value inherently pays for itself with the cost of that quantum improvement. Now, the last thing I want to leave you with before I conclude is that making an application in quantum happen is not just science, it's also an art. You want to be very niche with what need or limitation you're going after. You want to make sure that you have a scalable quantum algorithm that's not only applicable today, but will be modular in the future. And you want to make sure that your benefits are usable, they're accessible, they're explainable, and your differentiation has a sufficient moat. And if you bring these things together, no matter what you do, you have a very high probability of upside. If you look at the whole picture of where quantum commercialization succeeds, you want to have this really nice mix somewhere in the center where you reduce your exposure to competition, you have this high-value outcome, and you build a really large competitive moat. And it might not be always in the center of this circle between creating advantage for an application right on the right-hand side to having the right business model. It could also be somewhere outside there. But you need to figure this out as you build your applications, as you go to market. So what is the key takeaways from what I want to leave you with? One, donuts make hybrid real, and they're really tasty as well. Okay, they complete bringing together the best of the classical world and the best of the quantum world to make application-specific advantage a reality. Two, climate impact that matters is possible to quantum tech, and this has disruptive potential. And like we are doing today, now is the right time to start, because these things take time, these things need work, these things need iteration, but this is a very important problem to be working on. And lastly, it's not only important to showcase the advantage, it's not only important to showcase that there's potential, it is only real when adoption is achieved at scale. And the crux of driving this change is to make sure that whatever you build is productionizable. If it cannot be used by an end user, if it cannot be used in an industry that is dirty and archaic, there's no point in the solution, no matter how shiny it is. Thank you very much.
Well, thank you, Karen. Actually, could you leave the clicker on stage? But yeah, so Karen will be around during the whole event, so if you have any questions, I'm very sure he's happy to answer everything during the breaks. And during the long break after the pitches, he will also be at the table, so you can go there and meet him and talk to him and listen to more of this impressive stuff that he has to tell. But now it's time for the first pitch. So they are all still students. Can you click? I don't have a clicker. So you should see your team. No, it's fine. Keep it. Yeah, so all still students, but nevertheless already professionals when it comes to hackathons in the quantum realm. And 4/5 of them are here with us in Berlin live today. You can already come on stage. Yes, please. So welcome with me, Franziska, Katharina, Kevin, and Jakob. Together they're Team Quantumize. And yes, stage is yours. Time you will see over here. You have 20 minutes for your presentation. After 20 minutes, you will hear a jingle sound, and then I will come back on stage and we start the Q&A session. So thank you very much for being here, and have fun. Stage is yours.
Yes, thank you very much for having us here today and for introducing us. We are really happy to now open the round of the final presentations. And I would like to start with asking you a question. Did you ever feel guilty when you flew? I hope so, because you should. Air travel is responsible for about 2.5% of the global CO2 emission. And in addition to that, there are non-CO2 effects also having a negative impact on the climate. And that for pure luxury, because strictly spoken, you don't have to fly. Nevertheless, it is not nice to start a business trip or a vacation with a bad conscience. And exactly for this reason, Team Quantumized tried in the Deloitte Quantum Challenge to make flying greener with the help of quantum computing. We are Team Quantumized. Kevin, Katharina, Jakob, and me, Franzi. Jesus sadly couldn't be here today since he's from India and couldn't come to Berlin that easily. Together, we already participated successfully in other competitions, always with projects regarding sustainability application of quantum computing. For example, we looked into smart charging for electric vehicles or subsurface imaging for CCS. And now it's flight route optimization.
Yep. So let's begin by briefly revisiting the challenge. So over the past few decades, the rapid growth of the air industry has been a main contributor to the emission of greenhouse gases. During air travel, many different gases are emitted, and the contribution from carbon dioxide is known to depend only on the amount of fuel burned, and hence proportional to the time traveled. However, this is not a case for other gases. The contribution from other gases can vary a lot depending on where in space they are emitted. Sorry, where? Yep, and therefore the flight route matters. So the flight trajectories the airline companies are taking today, despite of being time efficient and fuel efficient, are not the most optimal for the overall climate impact yet. There's still a lot of room of improvement. And previous research from the German Aerospace Center has shown that with a slight change in the air trajectory, they can improve the climate impact by about 25%. We've implemented the algorithm they used and can confirm with that result. The problem they are facing is an optimization problem with big data, very complicated cost function, and many variables to optimize. And for such a big problem, it's very difficult for a classical computer to search for the optimal solution because it's too big. And the aim of the project that we've been working on, this Deloitte Quantum Climate Challenge, is precisely to see if we can take another step and further improve the results with quantum. So why quantum? Unlike classical computers, quantum computers can benefit from properties like superposition and entanglement. And these allow quantum computers to look for candidate solutions and evaluate them in parallel very efficiently, and thus could potentially lead to an advantage. And more specifically, we focus on the type of algorithms called NISQ algorithms. They can be realized in the near future. And if you look at the picture here above, you can see that we don't have much time left until the global temperature rises by 2 degrees Celsius compared to the pre-industrial time. And that would signify a large damage to the Earth's ecosystem and the population. And quantum computing, despite of its great potential, is still in an young stage of development. We are currently in this NISQ era where the available devices are of a few hundred qubits to a few thousand qubits, and they are noisy. And we are interested in solutions that can be implemented on such devices. Yep. And then for the process flow of the project, we divided them into two parts. The main part is, of course, the quantum algorithm used to optimize a single flight trajectory. And of course, we have another part which we made it the same for all quantum algorithms we choose. They include data cleaning, data visualization, and very importantly, check for error security. So we've looked into many different quantum solutions, including graphical solution, quantum genetic algorithm, the quantum neural network, and among them all, we think the most promising and interesting one is QUBO. QUBO problems are known to be NP hard on classical computers. However, they can be solved more efficiently with quantum algorithms such as QAOA, adiabatic algorithm, and quantum annealing. And we chose to focus on the QAOA method, and let's look at it in more detail. Thank you.
Yeah. So let me now introduce you to our QUBO solution, where QUBO stands for Quadratic Unconstrained Binary Optimization. I will guide you through our solution using this graph, and we will walk through it with a simplified 2D example first, and then I will hand over to Jacob, who will then show you an experimental realization on an IBM quantum device, and then also explains to you the how to scale up to 3D. So, first of all, we have to discretize our space or our cost function, which is a multiplication of the fuel we need and the atmospheric data. The fuel we need is for our 2D case constant, since we do no descending or climbing, and it's not depending on the direction we are following. We have discretized it in a way that we call these grids voxels, as in the 3D case, and we have used here a 4x4 grid. Our atmospheric data we assume to be constant during our flight. Yeah. So now we add some qubits. 1 qubit in each voxel. We assume our start point is in the lower left and our endpoint in the upper right. And we assume further that we have chosen a large enough grid that our flight route is really unlikely to have an optimized route which is not lying inside this grid. Next, we initialize our qubits. We initialize them in a way that our start and end qubit, as well as all inner qubits, are initialized in the superposition plus state. One border connecting start and end is initialized in the 0 state, here in red, and the other border is initialized in the 1 state, here in black. So now we have the qubits and our atmospheric data grid. Let's bring them together and combine them using a cost Hamiltonian, HC. We do this via adding ZZ interactions of neighboring qubits. So terms, they depend on the states of the neighboring qubits, and give them a prefactor. Here this B1, 2, an example for the qubit 1 and 2 case, which is just the average climate cost. You might wonder a bit about our naming style we chose. Let me enlighten you there. Our border qubits will stay constant over all our algorithm. Therefore, the ZZ-type interactions on the border will just be constant, and as one usually do, we will neglect them in the Hamiltonian. And interactions between the inner and border qubits, we can simplify them to Z-type interactions of just the inner qubits, and we will name the according prefactors then A. Now, therefore, we only need to consider really these four qubits we see in the middle, only have 4 qubits. And with this now, HC is an Ising-type Hamiltonian. We could use this on a quantum annealer, D-wave, solve it this way. Or, as Kevin mentioned, we want to use an analog QUBO to solve our problem with a QAOA on a real IBM quantum device. To be able to do that, we need to transform our Hamiltonian into a quadratic binary cost functions. We do that by replacing our set from before, which can have values plus minus 1, with binary qubit values, so 0 and 1s, where 0 stand for ground and 1 for an excited state. This form we can now feed into our QO and let Qiskit optimization solve all this via QAOA solver, and we do an optimization run. What we get back from this optimization run is a computational ground state of our HC Hamiltonian. And as a first step, we will just plot them here in the according color code, so 0 for red qubits and black the 1 qubits. A ground state will always have this form, the separated form. And we will now draw a line between the separations of 0 and 1 states. And it turns out that's all we need to do. If we now smoothen the separation lines, we have our optimal flight trajectory. Well, why is it our optimal flight trajectory? First of all, good thing, it connects our start and end point that we wanted. Then let's have a deeper look in this HC Hamiltonian. We have a negative sign. Our W prefactors are always positive, and the ZZ terms is positive if the neighboring qubits are in the same state, and it's negative if they are in different states. That means our ground state, which has all of the minimal energy, which is the realization of the minimal energy, divides us, our qubits, in two groups in a way that our line, our two neighboring qubits with very low W prefactor are crossed much more, the probability that they are crossed is much more possible than two qubits connected via a very high W value. Now we remember back that this W value was in fact just the climate cost. Therefore, in fact, we found a trajectory with the least probable climate cost on the way. And this is exactly what we wanted to have as our optimal trajectory.
All right. Then it's now my turn. Could I please get the clicker? Thank you very much. Because in the next thing, we wanted to take the math we just showed you to a real circuit, and that's what you can see here. We actually got access to the IBM Guadeloupe quantum computer, which has 16 qubits, and as you can see, we didn't use all because we reduced our problem to 4 qubits, and you'll see them marked on the left side. Katharina also mentioned that we are using the QAOA. Just to recap for a second what QAOA does, we have like this donut Karen told us today, like a hybrid solver which uses classical aspects and quantum aspects. And we kind of put the values in, get our quantum solution, and optimize our classical value set again, and repeat that for a quite long time until we get our desired result. And in this case, if we put our math into Qiskit, Qiskit will give us the circuit, and we can just measure it. And if you look here, you see what is the outcome of that. And that is our state 0, 1, 1, 1, I think, yeah. That has the highest probability and is our solution to our problem. And as you saw before, it's exactly the state you have in the grid. So the the Q1 qubit was in 0, the other ones were in 1. So we definitely get the solution we were searching for. And if you read our solution paper, you also see we tried brute force method to check that we did the right thing, and that did work out. But since it's only 2D, we are missing like a certain height, especially for airplanes. They definitely need to change height. And therefore, we want to introduce a third dimension in the 3D case. We want to make use of qubits, so it's like a qubit, but not with state 0 and 1, but states 0, 1, and 2, and can now get like 3 values. We can color these 3 values. I'll explain the graph on the left side in a second. We can use these 3 values now to color our stuff. The next thing we need to do is to slice our atmospheric data we have in planes like you can see here. And we can color the planes in the different values. And as you see here in the middle, let's see if that works. Yes. Here in the middle, where all meet, we get an active phase. And that active phase will be very relevant for us because if I do some clicking magic in a second, you will see what happens. I just add another plane, also with one active phase and 2 other planes. And if I click the next one, you will see we get a flight trajectory. And that flight trajectory is now a 3D trajectory, and depending on our algorithm, we will get a different style of each of the planes, so we can definitely optimize the flight trajectory for us. Wait, that was a bit too fast. If you now think about why is that actually the best flight path we can do. Each active phase we pass through adds cost to our flight. So if we have more active phases in one of the planes, we will get a higher cost. So our algorithm will be trained to reduce the cost, in this case, for example, to exactly 1 active phase. And I'm not quite honest to you with the flight trajectory shown here, because if you stack the planes together, you will get also, like, in between the planes, active phases. And those also add to the cost, because we said, like, where all 3 colors meet, we get an active phase. And that's also true for 2 planes getting together. So we also kind of ensure that our active phases in the planes here are not too far apart, but also close together to form a kind of cheapest trajectory we can get. So the last thing we need to do, which is shown here, we still need to know if you're cruising, climbing or descending, because we need the fuel consumption during this. If you now zoom into one of the planes, you can see here on the left, it's like a cross-section of a straight line solution. On the left side, we start our flight, climb up, cruise, and descend. And from there, if you zoom in, we can get, with a slight lattice offset, more like we can get these triangular prisms, like in a crystal where you have different planes. And from those, we can decide which plane or which planes we cut if we're cruising, climbing, and descending. So if we cut the blue and the yellow, we know we are climbing. If we cut the yellow and the pink, you know we are cruising. And if you cut the pink and the purple again, we know we are descending. And therefore, we can add, calculate all our fuel consumption and add it to our whole cost and optimize our flight trajectory. With this, I'll give back to Franzi for our pre-flight checklist and to summarize. Thanks.
Yeah, let us shortly summarize what we have achieved during the challenge. In the first chapter, we evaluated possible quantum algorithms with respect to our use case, and in our opinion, bringing the problem into a QUBO form and then solving it via QAOA is the most promising approach. We then performed a proof of principle simplified 2D experiment on a real quantum device and get the true optimal value. We then verified mathematically that what we have done was valid and then scaled it up to a 3D version. We think that it's legit to say that our work can be seen as a first step towards a full quantum solution for this problem. Nevertheless, there's still some work to do. For example, we would need to look again into the 3D integration. Like we said, we choose these prism cells as unit cells. We would to check here if other geometries are maybe better, and especially have to adjust the prisms since the rate of rise and descent are varying with the flight level, so the angle is not always the same. Also, there's always a trade-off between how many qubits you have in the grid and the precision of the result, and there to find the optimal value between what is hardware-wise possible and what we get would be needed to evaluate it. And also to take further effects into account, which come with certain restrictions like the starting and landing process and the time involving atmospheric data. And of course, the hardware always needs to scale up. We want to use Qubits. However, we are not worried about that since companies like Rigetti Computing is already looking into it because they are also connected with other advantages. For example, like that you can easily decompose 3-qubit gates on them. Here you can find 2 links in case we inspired some of you to look also into topics like this. One is to our GitHub repository where we stored all our code and work we have done during the challenge, and one to our website. And with that, we want to thank you very much for your attention and looking forward to your questions now. Thank you very much.
Thank you so much. That was really impressive. Thank you so much for your solution and yeah, for presenting this. So now it's 10 minutes time for question and answers. Who has the first question? Jan is already looking as if he, yeah.
So I have a question on the implementation that you have done. So you have shown the results on the real device, yeah? And we have seen that the optimal solution has the highest probability. Did you also run that on a simulator? And what is if we do not consider the effects of error noise of the real system?
Yes, of course, we first run it on the Chasm simulator, and it just gives the perfect results. I mean, like, there's, like, you will see a single bar super high and the other are just, like, flattened almost to 0. Yeah.
I think we included it in our report, the result from the simulator, and it was even better than this, obviously. So, yeah.
And did you try any error mitigation techniques on the real device then? Or was that not your focus?
I mean, like, we ran this on the Quadratic program provided by Qiskit, so, I mean, like, it didn't do it, but we also tried it with Qiskit's runtime, which was, like, recently developed, and the result was also very good. But we only did like readouts, error mitigation, yeah.
So, if I may, one other question.
Go ahead.
So, if I understood your approach correctly, then if you have in 2D an n times n grid, you need n minus 2 times n minus 2 qubits, right? For the 4 times 4 grid, you needed 4 qubits. So with the 16 qubit device, you could scale up to a 6 times 6 grid instead of 4 times 4. Did you consider that?
Yes, that's true. But like, you know, like with QAOA now, you know, like there's still a big challenge in the implementation part because, of course, like QAO circuits are very deep. That's why like some people are looking for hardware efficient ansatz, or like some like hardware software co-design approaches. Like a lot of research is still done there to like to run it successfully on larger scale. Yeah.
And maybe to also mention that we use the 16-qubit device and we choose the 4 qubits which are were connected the best for the interaction gates. So even if we could run it, it might not give the perfect result because, as you know, I don't know if you know the layout of the IBM devices, but there are some qubits very far removed, so get an entangling there would be quite hard to get, so we just choose the 4 best for our solution.
Yeah, that's good. Thanks.
Okay, next question. Henrike has a question? No.
Thank you for your presentation. It was very impressive to me. But I only saw one trajectory. I'm from an ANSP, a navigation service provider, so we are interested in what will happen if you have more than one trajectory. Could you go into more into details with this one?
It's true, you have that correct. We are doing more like single trajectory optimization, and what we have done then to see that the air security conditions are still met is we have first calculated a set of all the hundreds flights we were given, then checked the air securities, and for crashing flights, we just recalculated them, since these ansatz are not as in a way that they always give the exactly same route. They vary a bit, the solutions, and therefore we try to recalculate the solution or the trajectories which were problematic until we get a set of optimized flight trajectories that made that fulfill the air security.
Thank you.
And maybe just to add to that for a second, it's definitely not the efficient way to just recalculate all the flights that crash in that way, but it was our approach. If you go one slide before, that was quite nice. You can see that we kind of, yeah, exactly. There you can see like the flights we have kind of colliding or which violates the safety regulations, and we just do recalculations of each flight until, in this case, it worked out that we don't have any flights left. Maybe you can also do small changes in the flights if you know the exact path to overcome it a bit more efficiently, and then check the cost again if we are still on a quite efficient route.
Thanks a lot from my side as well for your presentation. You gave us an outlook what to do next and further improve your solution. If you need to estimate when we really could use it in life in real time, what would be your estimation?
I think it depends a little bit on the hardware development, and there it is kind of hard to give an estimation, I think. Like IBM, for example, published a new roadmap, I think 2 weeks ago, and they shifted everything by a year forward, so they have now higher estimations about the qubits. Rigetti Computing shifted it for a year backwards, so I think there are still some challenges which we are facing, especially when we want to use like this 3D integration where we have to rely on the Qubits at the moment. So I think it's a really hard estimation, but I think it will like take a decade until the devices are ready for that.
And if you could wish for something you would like to get to make it faster, is there something you see which would be necessary to implement something like that faster? As we learned, we do not have time, as you said.
Yeah, of course, a better or a faster hardware development. Like, I think it's quite hard to say it, or to estimate it there. But at the moment, the focus is on superconducting qubits, since they are most promising, and also a lot of the fabrication techniques are already good known from other industry parts. But maybe there are also, especially for the Qubits, other hardware solutions which can scale up further and be useful for our solutions there.
Thank you.
Yeah, and I would like to add on that point, like we are really lucky because QAOA is an active field of research, and like a lot of research can be done in terms of hardware, and you see in this problem, like this really maps well to the architecture of superconducting qubits, because like for IBM devices, we have square lattices of qubits, but like here the qubits are also placed in squares. Yeah.
Yeah.
Yeah, so many thanks for the introducing me. Personally, who has no idea how Quantum is working. But still, I would like to know, is this algorithm you've developed here, is it something which is already known to the community, or is it totally new?
I mean, like this whole idea of QAOA already started in year 2014 or so. Yeah, so like really a lot of research has been done and is still ongoing.
But I think the main challenge was to kind of find a solution for the challenge. And the main work was to come up with an idea how to map it that we can actually use QAOA. Because QAOA you can use when you have this cubo form, but the problem weren't like deserved us in a cubo form. So we had to think, and also with the 3D integration, it was kind of difficult to come up with a part and this prism cells so that we actually end up so that we could use QAOA. So the algorithm is there, and I think, or I would say it's also the most promising one for a quantum speed up at the moment for optimization problems, but one has to map the problem into a form where we can actually use this algorithm.
One more question. You did some simplifications like constant fuel consumption, then direction-independent efficiency, climate costs, and especially this on triangulation process that you've taken this constant climb and descent rates. How difficult would it be to extend your approach to have a more, to reflect the flight physics more cleanly?
So we are all physicists, and Gizar, he's also from the physics side, but he was our math guy. And we think that there we would need to cooperate from the math part, that they can really like perform a proof that this is the optimum and perform a full proof of the 3D scale up. We have done it for the 2D case in the report, but for the 3D, there are some parts which still need to be verified that they are optimal, or if there are like other geometries which are more optimal. And I think for that, a cooperation with students from the math department or PhDs there would be really useful, since they have kind of another view and also another look on the topic.
But to come a bit back to your question, we were actually given the simplifications that we just have one rate of climb and one rate of descent, and we were at least told that these are more or less already the optimized rate of descending and climbing, and also if I go to run direction in a grid, it does not really make a difference if I stay at a constant heights in which direction I'm going there. So that we took more or less from this challenge description. And
yeah, so some of the simplifications came from us as the challenge, well, authors. So because we wanted to have a starting point that people can reach a solution within these 6 weeks that we gave them. So, yeah. So, but thank you very much. I think there's a question from the online jury. So if you wouldn't mind to answer one more question, I would allow it.
Sure. Great. Yeah. Great. Thank you, Barbara. So that's from Patrick, from our external jury member. The question is, how is it guaranteed that the separation line, the optimal trajectory, is not in a way chaotic or zigzag?
That's the thing. We guarantee it because we add a cost. And because if the line is like a zigzag line, we will add more costs. The more unorganized the line is, the higher the cost will be. So we will smooth it out in our algorithm itself. And even after that, as we saw from Katharina in the 2D approach, we won't fly in a zigzag way in the end, for sure. So we still smooth it out. But I would say from the cost perspective we have, it reduces really to the most efficient way. And that surely won't be chaotic, because if you fly too far away from the path you have, the cost will just increase to a super high amount, and that is not what our algorithm favors.
Additionally, you will not encounter something like an island of 0 states in a lake of 1 state, since if you would put these 0 states to 1 state, then you would drastically reduce the energy of the state, since every border with 2 different states would add additional cost or energy to this ground state, and therefore it wouldn't be a ground state. So having a ground state already gives us that we really have this more or less separation into two areas and no single islands in between.
Understood. Thank you.
Thank you very much. And big round of applause, please, again, for our first team. Yes. So we will now have a short break. We already learned lots of things to discuss. So we will be back at some time, which is on the next slide. Yes, 2:45 p.m. Take a drink, relax, and see you back then. Hallo. margin of error, I would say, for flight. Well. Okay, that's enough people for me now. So the next pitch, so we will hear 2 pitches in a row now. So and the next pitch is from someone who actually entered this challenge as an individual, which I personally really admire. So he is a single-person team, and he came all the way from France, and I'm very happy that he's here with us today. So please welcome with me on stage for his pitch, Julien.
Hello, everybody. I'm also very happy to be here as a single person, as you said. So I will present my solution to this challenge, which is a graph-based quantum annealing method. So the general idea, the overview of the idea, for my solution, I wanted a simple formulation of the problem and of the solution also, as I like simple things. So this is what I wanted to do, and also something which could be formulated naturally, and also an efficient solution and a realistic approach, meaning that, if possible, that could be implemented and used now or in a very small future. So when I think about the problem, when I think about how to solve the problem, the goal for me was to find the trajectory of each flight, which reduce the climate effect. And I will call that the shortest path for each flight. And given a set of shortest paths for each flight, finding the flight that does not conflict with each other. So, as you understand, there are 2 steps. The first step here is to construct a graph which modelizes the map of Europe in a 3D, where each node is a voxel, and each edge is a possible route between each edge, between each node. Sorry. In this graph, we embed mainly all the constraints of the challenge, the atmospheric constraints, because edges has a weight which is computed with the characteristics of the plane, the plane, and the level, and so on. And each edge has also a time parameter. We embed the time required by the airplane to fly from a node to another. To solve this first step, I read many solutions to solve the shortest path, and I have seen that a gate-based method was not possible because it requires too many qubits, and the quantum annealer is well suited for this purpose. So here is more or less just an illustration of the idea for the first step. So you can see that given a start point, I think we don't see the yes, okay. given a start point and the terminal point, the goal is to find the shortest path, so the trajectory which reduces the climate effect. So each, as I said, already said, each node is a voxel, so latitude, longitude, and in a 3D for each level. And each edge of the graph is a cost for the plane to fly from a node to another. So the goal is to minimize the cost of the trajectory. For the step 2, the choice I use to remember the second step is to given a set of trajectories for each flight, picking each trajectory that does not conflict in terms of security of distance between each flight. So to do so, I use a method called the conflict graph method. And using the step 2 consists on building this conflict graph and solving the maximum weighted independent set. I will explain just after how it works. And the method, the maximum weighted independent set, is directly available in the D-Wave library. So just building the graph and then run the algorithm, and that's it. So this is just the illustration of the step 2. So you can see that for each flight, flight 1, 2, 3, you have a set of shortest path, and each edge is a conflict between the trajectories. And each node has a parameter, which is the cost of the flight, the trajectory. So the idea is to add an edge between each node of the same flight. They are dependent, and then to add an edge between between the trajectories of other flights that conflict regarding the distance between the distance of the airplane. And to solve the maximum weighted independent set, you will select one trajectory of each set of flight, and you will have a result that does not conflict. So for the implementation, for the shortest path of this first step, I wanted to implement a QUBO formulation inspired by the paper I read from Cross. This is the name of the author. But it differs slightly from the paper because just in the formulation, but the idea is as follows. In the path, I create some variables. Each variable has two information: the position in the path and a node that I put on the path. So, for example, the variable xij contains two variables, a tuple, the position in the path and which node is visited at this position. So for the second step, the building of the conflict graph is a classical task. Also for I don't know if I tell it just before, but building the graph is always a classical task. Donc there is nothing here quantum. but solving the shortest path or the maximum weighted independent set is a quantum task. As a result, the combination of these two approaches, these two steps, so shortest path and the conflict graph, can give the exact solution. The solution depends on the accuracy depends on the how the graph reflects to the reality, and it offers using two substeps offers some advantage. As at the end of the first step, we have an overview of all possible trajectories of each flight. Yes, and it allows to allocate all the QPU resources for one task instead of using a QBO which embed all constraints like time dependency, etc., which require a lot of number of variables, which is not satisfiable. And finally, we have seen that the proof of concept can give good result, and but the method I use for the QBO, in fact, there is three formulations of the QBO for the shortest path in the paper, and the one I used was the fastest to implement, and but is not the most efficient. The third one is the one we need to implement to be able to run the full challenge and being able to achieve our goal. So that's it for me. I wanted to thank you, Deloitte, and all the jury and all the participants. I'm sure that they all made great works, and I really enjoyed tackling this problem, this challenge, which is a very important challenge for the daily life. So thank you.
A lot, and it's now time for question and answers. Yep. So, who has the first question? Yes.
Yes.
Thank you very much. Very interesting. For the first step, is it possible that if you have, for example, a negative climate cost, negative objective function, that you sort of circle somewhere to collect all these negative values to get a low climate impact and then go further? So, for example, for your flight from Paris to, I don't know, to the east somewhere, so, to go first to Italy and circle there and then pass.
Yes, so I didn't mention it, but each age has a, yes, I tell it, but maybe I was not very clear. Each age has a weight which can be negative. Okay. So when the shortest path is computed, it is regarding the weight of each age. So at the end, we can have a negative impact, a negative weight. Yes. Yes, it's okay.
Yeah, thanks a lot for the presentation and for the solution. You mentioned that the problem is too large for a gate-based approach, but works on an ANILA. Is that a statement about today's hardware, the hardware that is available today, or also in general? And
no, no. In a near future, it could be possible to imagine an algorithm for the gate-based. Okay, but not yet. I speak for my solution, meaning that regarding the paper I read, the today's possibilities for shortest path computation, it is not. We cannot think about this solution, but in the future, why not? I think it's possible. Yes.
And is the formulation of the problem, is that suitable for a gate-based approach? I mean,
excuse me?
The formulation, yeah, is that suitable for a gate-based approach? So at the end, it's a QUBO, right?
Yes, at the end I use QUBO, so it's, it can be, applied for gate-based.
Right, okay.
But the advantage of using D-Wave is that they have many more qubits than IBM hardware, so it's easier to implement, and yes.
So you have to be faster, Jan. We heard that in the other pitch as well. So it's
I have a question about the generation of the shortest path. So the set of the shortest path for the single flight. It is a challenging work, and my question is, how did you assure that the path has really significant deviations? Because there are examples for sure where you do, the flight is just doing a short detour, and this detour is in the wrong place.
Excuse me, can you reformulate your question, please?
How to assure that the path of a single flight deviates significantly, so they help to solve the confliction step?
Okay. The graphic construct regarding all the constraints, as I said, and the edges really how to say really give us an idea of the possible trajectories. So given the constraint of the so the angle of turn, the descent, and the climbing. So there is no possibility. I don't know. Sorry. I compute the weight of the edges according to the airplane characteristics. So I know flying through two nodes of the graph, I know that each node has is a latitude, longitude, so has a climate, atmospheric information. So when I construct the graph, I take in account this information to have a weight for the edge that correspond to the reality. I don't know if it answers to your question, but
I'm not sure how to rephrase the question.
Okay, I'm sorry.
I'll think about it.
Maybe we can use the break then, and then the two of you can discuss it a bit further. Yeah. Other questions, Andrea? You look like you have a question.
Just for me, and we have to go. Thanks first of all for your presentation. And we have to go back really to the beginning, because you said QUBO is the only solution you could choose. But could you explain, just for me, and I'm not a quantum computing expert, why you came up with QUBO? So what else did you try or looked at, and why did you choose for that?
Yes. Okay. There was other approach which could be possible for the shorter space, like random walk, for example, where your algorithm try every possibility randomly until you find the good solution, more or less. But also it use this algorithm require too many qubits also for our problem as we have many constraints. So it was not for me realistic to use this possibility. So yes, I think about other possibilities, but for me it was my idea. For me the better idea. But
so that's the one and only, basically.
Excuse me?
That is the one and only, basically, from your perspective, you choose now.
Yeah.
Okay. Maybe can I add another question? you said you like simple things and you like simple solutions. And the optimization you did, you described, as far as I understood, that you avoid a collision between planes simply by getting them another path, but not necessarily let the plane start later or get in another altitude. Is that correct? So you simplified your model by I simply do not, or I take out.
No, in fact, all information like timing information, like time of start and of each flight, can be taken in account when constructing the conflict graph. This is a part that is not be done in my document because I don't have the time. But it also classical computation, I could say. But when I construct the graph, the conflict graph for the second step, I take the time of departure of two flights, for example. Then I know which edges he will pass through, and I know also how many time it takes for the plane to go from a node to another. So I take in account the time of the departure, and yeah.
Okay.
So I know at each moment where is the flight, when, and if it conflicts.
Thank you.
Okay.
Thanks a lot.
Just a quick note for the technical. We lost the timer on this screen here. I don't know if it's possible to fix that. Yeah, because so that our next pitch knows how long they have. During the time that we fix that, I actually have no idea if your 10 minutes of question and answers are up or not. But I actually have a question for you as well, because I think I read in your solution that you said you're not working on quantum stuff professionally at the moment, so you do this just for fun.
Yeah.
Is that correct?
Yes.
So how come? I mean, I applaud that, but
Yeah,
how do you do quantum just for fun? What's the story behind that?
I think I could say that I started to be interested in quantum computing since 2 years ago. And since 2 years, I try to learn quantum computing as everybody, I could say. And and last year, so I restart my studies and I validate a master degree in quantum computing. And next year also, I participate to other challenge, IBM, for example. And I won the hackathon France for the French zone. So yes, this is my hobby for the moment.
Very cool. We need more people who do quantum just for fun.
Thank you.
Okay, so speaking time has been exceeded, so thanks again. And it's time for our next pitch. So while we had somebody now on stage who does quantum just for fun, the next team does quantum for professional work, I would say. They are from Lufthansa Industry Solutions, and they gave themselves the very catchy name, Quantumverse, Lufthansa Quantumverse. So very happy to have you here as well. And your time starts at some point. Hopefully you will be able to see this on this screen. And yes, thank you very much. And big applause, please, for Lufthansa Quantumverse.
Yes, thank you, Barbara. Thank you, Deloitte, Quantum.Link, and the KI Park for having us. Of course, also have the jury. Thank you for having us here. We are Lufthansa Quantumverse, and we actually are part of the AI and data analytics team at Lufthansa Industry Solutions. Started at the end of last year, building our quantum team, and kicked it off really at the beginning of this year. Obviously, this quantum challenge fits really well into the problems of Lufthansa as a company, and also the topics that we look at as the quantum team within Lufthansa Industry Solutions. We look at quantum machine learning because it's very close to all our other use cases in AI. and then also scheduling optimization problems, gate assignment, warehouse logistics, for air cargo, but also outside of that domain, flight schedule, and then flight path, which is what we're here to talk about today. Georg and myself, Josef Deutsch, are here to present our team. You see we have 5 people. The others couldn't make it to Berlin today. Now, the Quantum Climate Challenge has been introduced a couple of times today. What I'd like to highlight here is that we have this CO2 part, which is discussed a lot in public. I think the German Aerospace Center does a lot to actually also bring those other non-CO2 topics in awareness and look at those. And actually those, especially the water vapor and then NOx emissions, are discretized or change in time and space, but they are still varying smoothly, as does the CO2 emissions. And then in addition, we have the contrails, which form only under very special physical conditions. So the air needs to be quite cold and really humid or really wet to actually even have the possibilities of having these contrails. And if we have those contrails, they are very localized, and the areas are localized, so it's actually easier to avoid those. For all the others, it's actually easier to find an optimum. And looking at the data that we got for this challenge, we can see that here the sweet spot actually is at about 7,000 meters altitude in terms of emissions or change in global temperature. Now, the fuel consumption actually decreases with altitude. So we have so that's why actually airplanes fly above 10,000 meters right now. But still, even combining this change in temperature and the fuel consumption, the optimum to fly in terms of climate change would be somewhere around 7,000 meters. In the turning plot there, you see actually a visualization of the places where the contrails could form if we would fly through these areas. So these are the ones that we would want to avoid. Now, we split up the problem into single flight and also multi-flight solutions. And this makes sense from splitting up the problem, so to have 2 easier problems to solve, but also actually because the first part, finding the optimal flight path for individual flights, is what the airlines or the flight planners actually do. And then the second part of finding a conflict-free solution from those multiple individual flights is what air traffic management does. And for the first part, for the single flights, we actually had 3 solutions. The first one is classical, so actually introducing a chosen number of points. We actually chose 7, and then optimize those points along, or build a trajectory along those points, varying those to optimize the climate effect of each individual flight. Then the Qubits solution, routing on a cost graph, which is actually very similar to the solution that we saw in the previous pitch. And then the gate-based approach, which Georg will introduce in a minute, routing on an implicit cost graph, which is actually a solution optimized for a gate-based quantum computer. And then conflict-free solution of single flight solutions, we'll see, is also through a QUBO approach. And we are actually working on an approach to combine route optimization and conflict avoidance, although I'll only give an outlook on this today. And with this, I'm handing over to Georg.
Yeah, hi everyone. As Josef already mentioned, we have a classical solution for the single flight, pretty much, for the problem basically saying finding the trajectory of an airplane that minimizes the basically the emissions. And in order to lift that also to the quantum computer, we had a few thoughts on how to do this on a gate-based quantum computer. And we basically looked at the problem in this form. So we discretized the flight of the airplane by a graph, basically having the airplane starting over here, and then kind of the nodes of this graph, and they basically represent all possible locations of this airplane. The edges then representing moves of the airplane up to the destination. So the nodes represent the locations, and we have a few constraints here. That is that the airplane can, of course, only move in with certain maximum inclinations. So this graph is sparsely connected. Like in this case, we basically limited the amount of allowed moves to 3. And the graph is, of course, strictly directed because the airplane can only move forward in time. Then we can sort of project the problem onto this graph by saying each of these edges actually has a cost function contribution. So moving from one location to the other has a certain, basically, emission load. This is shown here on the side. The numbers are not really important. That's just that we basically also had to perform a bit of a normalization to these values in order to be able to put that into probabilities on the actual gates. Yeah, then we can discretize this in a circuit, basically. This is the full circuit, the full final circuit that we came up with. I think, interesting here is that you can sort of see this cascadically activating the qubits, which allows us to kind of basically impose this direction of the graph as well as limiting the amount of allowed moves. And this graph, or this circuit, should be designed such that it oversamples the climate optimal solution. So it's not a random walk, but it should sort of, yeah, oversample the solutions that we actually want to find. If we dive into one of these building blocks in the graph, in the circuit, you can see that we kind of do this by these multi-conditioned NOT gates. This is the example on for going from node 4, where 9 and 8 are the allowed moves, and you see that we condition the move by this particular node 4, and then we allow that you can go to node 8 or node 9, and we apply these rotations based or conditioned on the cost function value, such that this particular move is more likely if the cost function contribution here is small. So we ran this on a simulator at first, and we could see that we're actually indeed oversampling the good solutions. The one that's highlighted up here is the one that indeed has the, so when checking this classically, that has the smallest cost function value, and we sample this with a probability of 80%. The cost of this algorithm is that we need 1 qubit per graph node currently. So of course this also grows as we allow more potential locations of the airplane. So we're indeed oversampling the paths, and this also minimizes the number sort of null paths or of not useful paths in the sense that we mapped the 2 constraints into the circuit to directly represent that. Optionally, we have also implemented or we had a few thoughts on, you could actually also evaluate the cost function on the fly here on the quantum computer, if that would be necessary. And in terms of, we can probably reduce the requirement of 1 qubit per graph node by saying we make this an integer encoding instead of a 1-hot encoding for the graph layer. Then, thanks to IBM, we also ran that on the Guadalupe, which is a 16 qubit machine, the very same problem. And we also saw here that we're oversampling basically the paths that have the smallest cost function value. We're here in a lot, like the counts are a lot smaller. There's less shots, but these are sampled at the highest probability among all of the solutions that are being found. And we have 8-second walk clock time here versus 30 seconds on the simulator. So even for that very small problem, that was already a good speed up. And sure, we have fewer valid counts than on the simulator, so we have the problem with erroneous or error correction here. Okay. And with that, I hand back to you.
All right, thank you. Yeah, so we saw one of the 3 possible solutions, or one of the 3 solutions that we actually introduced in our paper, just introduced. Any of those can now be used to actually create the multiple flight solution. And the idea here is that we actually create multiple variations for each flight. So basically having several options that all get close to the optimum of climate emissions for this individual path. And any classical or quantum algorithm can be used for this. And this ends up being m to the power of n combinations in total, with n the number of flights, m the number of variations. So here actually we could have potentially even 10 to the power of 99 combinations of routes with 99 flights and 10 variations for each of those 99 flights. Of course, we wouldn't want to go through all of those different combinations. So what we actually do here is we create a list of all possible collisions. And this just, we do this pairwise. So actually this ends up being n squared half evaluations here. And then actually build a quadratic constraint model to find the set of conflict-free combinations, and amongst those conflict-free combinations, actually select the one that minimizes the emissions. And here we need, for this quadratic constraint model, or also mapping it to a QUBO, actually n times m, so the number of flights times the number of variations variables. And our cost function that we are minimizing is actually here. We have the cost function value for each of the routes. So these are the emissions or the change in temperature for each individual route. And then we have the constraints back here. And those constraints are always 0 for any combinations of routes, except if 2 routes actually belong to the same flight. So we, of course, want to have only one variation for each of the flights. And it's also non-zero if there's a conflict between those individual routes. So let's have a look how this actually is implemented. Here you see the actual solution for using the CQM D-Wave method. And on the right here, you actually see just very simply how those objective functions are included here, and then we have those choices of one route per flight, and then in the end here, the constraints. Now this then maps into a QUBO. Here in an example, just with the 3 flights and 3 routes per flight, and just for illustration, with no conflicts to start with. And this actually turns out to be we have this Aero values here for always the same, or the penalty term, always if we have the same for all routes of the same flight. And then actually have here half of that lambda negative plus the cost function. So you can actually see the best flight here. I think lowest cost function is at 11, which this is also the one that actually has the lowest value here on the diagonal. Now, if we add the constraints, what the CQM actually does is including slack variables. So we actually have at the expected point, so here for the collisions between flight 00 and 10, exactly at that point we have a penalty. And then actually adding a slack variable for each of those inequalities, just saying that basically these 2 variables summed up should be 1 or 0. We actually, since submitting the paper to the challenge, actually found a solution where we can actually embed all of this into a QUBO where we don't actually need those slack variables. So then actually here the number of variables would increase with more conflicts, so it wouldn't scale ideally. In our new solution, we can actually do without those slack variables. Now, our results actually show that we can reduce the emissions for the example of the challenge by 11% compared to the baseline. So basically, just just using the direct route at the start level that was given. It actually also turns out that for this problem, the ideal path for most of the flights is actually to move to this altitude of about 7 kilometers and then actually stay there and take more or less the direct path. So we did combine linear flights, so basically climbing or sinking to whichever level the best solution would be. And then just staying there, and also this piecewise linear flights, our classical solution, to actually have any variation there, but even those mostly converged to the direct route, which also makes sense. Taking a detour only really makes sense if we would really avoid those contrail areas. And the approach introduced previously wasn't included here. As for the gate base, we can't really model here the full scope, just as you saw with those 3 layers, but it could be included at a later stage. Now, this is an animation where you see actually with these 3 time steps how all of those flights are moving through. Let's have a look at this again. So you see that actually the flights are avoiding the areas of potential contrails. Now, as an outlook, we are working on a way to actually combine single and multi-flight solutions, also using the constraint quadratic model, where we actually discretize the areas of contrails through ellipses so that they could be included as quadratic constraints, and then optimizing the routes and the conflict for finding conflict-free solution at the same time. The classical computing efforts in this case would be minimal, and yeah, as I mentioned, the emission minimization would happen on the quantum computer along with finding the solutions at all. Yes, with this, it just leaves me to summarize. Georg introduced the single flight solution optimized for gate-based computers and actually also run on the IBM quantum computer. And then for the multi-flight solution, we formulated this as a QU and have a solution run on the D-Wave Anila, which actually reduces the emissions by 11%. I think in our submitted paper it was still 7%. We came up with a better solution since, so now solving this by 11%. And I think with this, I thank you for your attention, and we're happy to take any questions.
Thanks a lot. 10 minutes of question and answer. Obviously, I have to ask the question of you're from Lufthansa Industry Solutions, and we have somebody from Lufthansa Systems in our jury. What is the relation? And will that give you an advantage? And hopefully the answer is no.
We did indeed meet here today for the first time, and not only in person. We had no conversation prior to today, so there is no link whatsoever. Lufthansa Systems and Lufthansa Industry Solutions are separate companies, and yes, we did not interact prior to today.
You can confirm? Yes. Perfect. Okay. Then I open the floor to other questions.
Thanks for the very nice presentation. Very interesting. You said you have 7 or maybe it was 10 nodes to calculate the trajectory. Is that also including altitude variations? I wasn't quite sure about that. And if you're stressed that the contrail climate costs are very patchy and could be very small, what would you think is a good number of nodes to really represent all of these small-scale structures?
So it represents altitude changes. Basically, each turn is described with 2 angles. So it's an in-plane angle and a height change if the aircraft wants. How many nodes is a good question. I mean, optimally, you want to converge to infinite resolution here, right? This, I guess, practice will tell, I guess, how many you need.
But I think one important part here is that the climb and sink rate were given. So basically, the algorithm is allowed to actually give arbitrary altitude changes. But then what the algorithm actually does is it climbs or sinks to the specified altitude, and then actually continues at that level. And for calculating the climate effect, we not only take the values at the nodes, but we actually do a much finer integration along the entire flight path. So if between two nodes there is a spot where contrails would form, this would end up in our cost function, and this would still be avoided. But as Georg said, both parts, so the number of nodes that are optimized and then also the integration path can be chosen freely, but especially the integration number can be almost arbitrarily high because it doesn't really give much cost, computational cost.
Okay. Yeah, thanks a lot for the presentation. If I remember correctly, in the solution that you submitted after the first round, you said that it would be good if you had access to a 12-qubit system to run additional or to really run that. How did that work out?
That is what we presented with on the Guadalupe. So indeed, we reduced it. We needed 11 qubits in the end. So 5 of them were not used on the machine. And then, can we go back to the counts? That was pretty much the result table that came out. So it worked perfectly well, running it. And our sort of the circuit that it oversamples good paths also still did hold, but not with the 80%, but more with about 5% in that direction, and then going lower. So it found a lot of solutions that are sort of, well, kind of not allowed. Okay. And I mean, an effect of the real systems is error and noise. And did you apply any techniques to mitigate errors? And we just got access, like there were a few problems with project IDs apparently, so we only got access a few days before, and then we couldn't. Okay. We were happy to run it.
Yeah. Sure. Okay.
But I think the good news here is really, as it was already implemented in Qiskit, really making it run on the actual quantum computer versus the simulation was basically changing 1 or 2 lines of code. So it was as easy as that once the project ID was sorted out. But
okay. Great. And the code, is that available? Have you published the code? Or is it more like code snippets? Or is it really ready to go? Someone else could also execute that?
It has not been published yet, but we will publish it. Yeah, it will be available after the challenge, absolutely.
Okay. Okay. And one final question, if I may. So it sounded a bit like the constraint quadratic model. Yeah, that is limited or can only be implemented on an annealer. Is that correct, or can it also be done gate-based?
Absolutely not, and I guess we saw that in the very first presentation. So we did solve it on an annealer, but using QAOA, it could be solved on any gate-based computer. For the problem that we had here with basically those 10 route options for the 99 flights, we actually end up with 1,000 by 1,000 size matrix, which would need to be solved. So the gate-based computer would need to grow a little bit until we can solve that. But yeah, absolutely, it could be run on any gate-based computer.
Kind of have the feeling that this keeps to be the answer.
Well, the roadmap is there, so
yeah. Okay, next question. Yeah.
Okay, maybe, sorry for the naive question, what is oversampling?
Just to sort of, that this particular graph appears more often in basically in the shots, basically when you solve the circuit. So if that would be perfectly random, you would sort of get all possible combinations, right? Or possible, so if all the probabilities for all the qubits would be 50-50, then you would sample all of them equally in an ideal world. And oversampling means we're conditioning it on the cost function value to have the probabilities reflected in there, such that we have a high probability to sample the paths basically that we want to find that actually minimize the emissions. That's what I mean with oversampling.
Okay, great. Thanks for the answer. And I'll try again to repeat the question from the previous pitch. how do you guarantee that you have enough path in the first single flight calculation to generate a feasible solution in the multipath approach?
So in the multi-flight approach that we presented here, we don't. Yes, we did find, I think, 33 solutions out of all of those that were conflict-free. But this is also the reason that we actually developed the last approach that I just gave a little glimpse, where basically we are optimizing the routes along with the conflict avoidance. And we also have some additional ideas of, so if there's no conflict-free solution, still the solution with the minimum number of conflicts should be chosen. And then if it's only a conflict between two flights, then one can also, in the post-processing, adapt the one flight to then come up with a conflict-free solution. So these are the two approaches that we pursue there.
Thanks again for the presentation. You started in saying we talked a lot about CO2 emissions and you focus on contrails. Can you repeat for me why contrails and how long are you working already in emission reduction for an airline? I mean, basically having Lufthansa Industry Solutions or being Lufthansa Industry Solutions, it's probably not your first optimization on emission reduced traction.
Well, actually, for our team, it is. So, I mean, in the data given for the challenge, the contrails, I think, were at a value of about 30, while all the other emissions were, I don't know, somewhere around 1 or 2 or something. So it was really a large factor higher for the contrails than any of the other emissions. But answering the question of, yes, we work on optimization problems, but we are the IT part of Lufthansa and Lufthansa Industry Solutions. So we work a lot of AI problems, but actually reducing flight emissions has not been, or we've not worked on projects in that relation.
And will you keep working on this now?
Absolutely. So we actually do hope that this is a trigger to actually collaborate with Lufthansa Systems on this topic.
Oh no! Okay, stop talking now.
Yeah, good.
Other questions that are less, well, other questions, please. Oliver, you had a question earlier, I think, or otherwise Volker.
Back to the oversampling. So you said that and you also showed that the differences between the individual solutions is not that big, 5-point-something%, 6% or so. Imagine now that the data from the client signs are having quite some uncertainties, and you overlay that within a field of probabilities. Would you run then into a problem that these small differences between the individual solutions are getting too small? No answer allowed, no?
Yes, answer is allowed. Of course, I allow it. I allow it. Mm-hmm. Oh, I feel so powerful.
Well, we're oversampling not only the one single best solution, but also any good solution is oversampled. So basically, we would hope that and then in the post-processing, we can still look at the best solution, and then basically also maybe there are other criteria for air traffic management or so that could then be included in that post-processing. But the idea would be that the best solution also maybe with other constraints would be amongst the ones given to us through the algorithm.
Okay, great. So thank you again very much. Big hand of applause. And after these two pitches, we will have another break that will again end at some time. And we will be back at that time at 4 p.m. here on stage with the final two pitches. Thank you very much. See you later. Okay, ladies and gentlemen, it's time for our last two pitches. And first up, we have a group of, let's say, classical developers who moved quantum for the first time, as I understood, for this challenge, which is also something that I really like. And they have the cool name Team Pluto, so I hope they also explain why they chose this name. No? Okay, then I leave that to the question and answer section. Please welcome with me on stage Team Pluto, Keno, Henrik, and Dominik.
Yes, perfect. So thanks for having us. We're very happy to be here. Yeah, we chose the name because we like the planet, so there's not much of a story there, but let's take a look at who we are. So first up, we have Dominik, who is currently a PhD candidate in Munich. And he's also looking for a job when he's finished. So in a year or something, you can definitely snack him up. Then there is Jonas, who's unfortunately not with us today because he has a scheduling conflict, but he'll be here later to mingle with us and you. Then we have Henrik, who's currently working as a software engineer at Hensoldt. And then there's me. I have my own little software development startup. And yeah. So what brought us here? We're a good group of friends, and we all share our deep love and interest of tech. And obviously, we're also interested in the future of our planet, as everybody should be. And quantum computing is one of the technology that excited us the most in terms of what potential it has and what it can bring to our society. And so we thought, why not jump on a challenge and use it for a good cause? We will skip over all of the preamble and explaining the problem here because we've probably heard it a couple times already, so we go straight to the solution. We used a classical algorithm to optimize a single flight path for the minimal impact as a baseline. So here the idea was that we would generate a lot of flight paths individually and then later on use a quantum approach to optimize them a little bit, as I said here, with solving the collisions in the high density areas where we know the flights will go based on the optimal weather patterns. And we have our quantum states that represent active and inactive voxels, so this one-hot encoding. And we defined a couple constraints here. And the goal, again, was to optimize on the climate costs. But we will now go into a bit more detail. First, we will talk a bit about the classical algorithm. Sorry for that. I know it's a quantum event, but it's part of our solution. And the idea here is really like have it as a proof of concept and see where we can go with this. What is the minimum thing that we can achieve with this? And we used the well-known greedy algorithm for that, basically just picking, when you are given a set of decisions, just pick the best one at the moment and continue on with that. It has quite a few downfalls that we've already outlined in our paper, but for this purpose, it was the simplest possible approach that we could take. We implemented all of the constraints that we were given. The only one is that it's only a single airplane. So we are not looking for collisions at the moment, but all the flights and climate, all the descents and turns and the climate values are correct based on the paper. And here, as a simple explainer how the algorithm works, for each airplane, we just had a couple of decisions to make. So basically turn right, left, up, down, or keep cruising. And we looked at it for what would it be in 20 steps in the future when we chose this route and then tried to pick the best one on that. We introduced a couple penalties to keep the flight on track, to not get stuck in some local minimas or something like this. So we rewarded it as it comes closer to the goal and penalized it a bit when it went out of bounds for the map. And then you just repeat this process over and over again until you reach the goal. And here you can see an example of this. So generally you would see the straight line. Here you see 2 times. So this is the morning pattern, the weather pattern, and this is the noon weather pattern. And the flight takes slight deviations. And on average, we were able to achieve a 7% improvement just with the classical algorithms compared to a straight shot at the goal. And yeah, now we're going to get a bit more into the exciting quantum tile.
Okay, I'm talking about a theoretic description of our QUBO algorithm. But first of all, I will have to talk about constraints, because we are using constraints to program our quantum manila. And here you can see the QUBO matrix. You have already seen that before in various other pictures. And here you have x1, x2, x3. These are quantum qubits. And in the matrix, you can see the constraints. Negative values represent a negative energy. Positive value represents a positive energy level. And this formula is the overall energy level of this of our program. And what a quantum manila is doing, it is minimizing the overall energy level. And with this program here, in this really simple program, you can prohibit selected states by making it impossible for 2 or more qubits to be won at the same time. And you can extend this program for more than 3 qubits, obviously. And this is like the main concept of our, like this kind of algorithm. We really need that a lot for our solution, what you will see in the next slide. But first, I have to talk about the state space, because we want to have 1 qubit for every possible state of the airplane, and this means the location the airplane where it can be located, the maneuver it's doing right now, and the time. The time component is really important because of collision avoidance, because we want to know where the airplane is located at a certain time so it doesn't crash with another airplane. And we also need the maneuver, decline, climb, and cruise, because all of these have a different climate impact, so we also have to consider this. But we have limited number of qubits in our quantum computer, so the values need to be discrete, but they still need small enough so our solution will make sense in the end and will provide a good solution. Then here you can see the rules for a single airplane. And first of all, we have 1 airplane per time slot. So I described the state space before, and you have all the possible locations. And at a certain time, there should only be 1 airplane, because otherwise there would be suddenly 2 of them. So we forbid that. And to do so, we need like this kind of algorithm here, which is forbidding 2 states to be 1 at the same time. Then the next rule that we need is each time step, the airplane can only move to one of its neighbors. And again, we can do that with such a logic, more or less. And then the airplane is located at the start position at t equals 0. That's also makes sense. And once the airplane reaches its destination, it has to stay there until the end of the calculation. And in the end, it will receive a high reward, so it will actually go there. And then, of course, we need to calculate the climate impact for a certain time, a certain location, and a certain altitude, and a certain maneuver, of course. And this can be represented when you normalize these values between a value between -1 and 0, and you can change these parameters over here to these values to represent the climate impact of flying through this particular voxel. And with that, you can optimize the trajectory of a single airplane. But you can also extend these rules to make it possible to calculate it for more than 1 airplane. What you have to do there is we have to add an additional state space for each airplane, and we have to forbid collisions. Okay. Then now we have this huge state space, because we have for each airplane we have a lot of locations, we have a lot of time spots, so the search space is really big. So what we want to do is we want to remove illogical parts of the state space. What we thought about, like in the beginning, when the airplane is departing, it will be close to the starting point, and when it arrives to the destination, it will be close somewhere around the destination. So you can remove some of the state space. Exactly, and you could do that with a classical algorithm, but you could also do that with a quantum algorithm. For instance, you could start your calculation, and with a small resolution, and then get rid of illogical parts of the state space, then increase the resolution, and do that procedure over and over again until you get a really smooth line through the time space, more or less. Yeah. And we also need a clustering algorithm, because when there are a lot of airplanes, a lot of them will not interact with each other. So you can build several clusters of airplanes which are optimized separately. And with that, we can actually calculate the optimal solution for several airplanes. And now I want to talk about the expected number of required qubits for our solution. When we consider, like, we have 3 airplanes, we have 100 time slots, we have 10 different flight levels with 300 meters each, X and Y positions, 10 of them, and possible movement 3, like decline, descent, and cruise. Then we can calculate the total number of qubits that we are needing, and this is roughly 1 million qubits. That's quite a lot, but these qubits are not fully connected, so that's a good thing, because also the hardware is not fully connected. For instance, the D-Wave Quantum Annealer right now has 5,000 qubits, which are also not fully connected. And if you are assuming Moore's law for quantum annealers, which says it doubles the number of qubits every year, then we can get over 1 million qubits in 8 years. Yeah. So the next part will be presented by Dominic.
Yes, thanks. So now we've talked about what's the background, and now I want to show you a little bit how we implemented this. And I want to preface this by saying this is really just a proof of concept. So this is a very early implementation just to show, in principle, it is possible to use this kind of algorithm to tackle this problem. But this is most certainly not the ideal or finished implementation. So we decided to go for the D-Wave systems, as we already discussed that it has a quite large number of available qubits at the moment compared to other platforms. And this is also the reason why we want to really use this quantum annealing approach, because it's also really widely used actually for this kind of optimization problems. And it, as we already have seen, it gives us basically 5,000 qubits that we can play with, and we don't really care in our system that it's not fully connected. And so we have this D-Wave systems quantum annealer where we can see the architecture here depicted. And it gives us basically, again, these 5,000 qubits, 35,000 couplers, and 15 couplers per qubit. So how do we implement this? We have heard about this basically before in other pitches. We also use a constraint quadratic model where we've talked about the constraints that we used before. So there are also, so it's basically like that how the airplane moves and how they avoid each other, et cetera, et cetera. And then we give it a bias in form of our cost function using the climate costs. And then we use the leap hybrid CQM sampler, which basically then allows us to intelligently allocate the quantum computer. So what do we get from this? Using a very, very simplified problem set with only 8 times 6 times 3 voxels and 4 flights, we get this kind of result. This is not using any collisional avoidance yet, but that can also in principle be implemented. And we can see here how we can basically get a few flights working, which move around and get to their destination. But again, this is not fully optimized yet, but in principle, one can implement this kind of algorithm. But we want to also show now is how does this actually now compare to other classical approaches, in this case now another constraint-based implementation using Google OR tools. In principle, we can basically use the very same constraint that we also use for the quantum implementation. So we can also use a constraint-based set solver for Google OR tools for this, and this actually is very, very good in terms of performance for these kinds of constraint-based problems. So we don't perform any mapping to airspace coordinates here, and how well this actually works in terms of runtime also depends on the hardware, et cetera, et cetera. But to just give you an idea of what happens when we use this, so we can basically now look at, for a given number of voxels, how do different times of or different parts of our algorithm actually scale. And what's actually kind of interesting about this is that in this case, the cost function is actually the most costly part, which is not what we initially expected, and the solving is actually basically trivial, at least for this amount of voxels. One shouldn't really take those execution times here very seriously, because this is run on very primitive hardware, basically, and this should just give you an idea on what's the scaling that we could expect here. And now the question is, can we actually use this also now for the full algorithm? And so we get basically these kinds of trajectories, so either for a single plane on 10 times 10 times 5, as implemented here, or for 4 planes on 5 times 3 times 3, which here does have illusion avoidance and full time independence. So this is optimized on the cost function in terms of the climate impact, and basically in this way optimizes the performance fully on this kind of very, very small system. So is this actually now better or worse in the quantum? So is it worth using quantum in this case? So far, I would argue actually no, not really. The hardware is not quite there yet. But because we see that, I mean, D-Wave has basically these 5,000 binary variables that we can use, and we basically have here now 192 voxels and 4 flights. Google R2 actually is in this case a lot better and allows us to basically implement a much larger problem space. But of course, this also depends on the scaling, on the expected hardware changes, as was already discussed before. And with that, I want to go to our outlook and to our summary. So basically, we've seen that these kinds of quantum computations are very, very hard, and we're really limited by the available hardware today. That's very obvious, I think. But the question is now, can we really now combine the advantages of quantum and classical? And I think this is really the main property of our approach here. We're using a hybrid algorithm to really take advantage of what classical and quantum algorithms both can do. And the good thing is now we can actually scale this, because we can basically freely decide how much we want to do classical and how much do we want to do in quantum space. And depending on what's the available hardware, basically, we can then choose to do more parts of the algorithm actually in a quantum way. And in the end, if then the hardware would actually allow it, it might actually be then possible to run the full system, the full problem set just on a quantum system, but obviously not quite there yet. So yes, and then we can really adjust this mix to what we want. And with that, I want to thank you for your attention and look forward to your questions.
Thank you very much. Yes, questions, please. We start at this end again, or yes? No? Okay, middle.
The middle.
Yeah.
Thank you for your work on your presentation. Very, very impressive. Very different solutions. I have a question to the last presented solution, the classical one with conflict avoidance. Sometimes it's difficult to see this in a 3D view, but did I see vertical parts of the trajectory? On the right-hand side, the blue one, for example. At the end, it looks very vertical.
Yeah. So what happens here is basically this is on a voxel-based system. So we didn't smooth the path, and this is modeled as an incline. And here, when we would look at the costs, we would then get a smoother functions. But for the visualization purposes, we have like very big cubes here, and we're just drawing to the center of these cubes, which is why you will see a straight up. But okay. In reality, it's
in reality, not every airplane can do this kind of trajectories.
Yeah, it does look a bit unhealthy from here, yeah.
But you can really easily change the things which are allowed and which are forbidden, and yeah, so you can actually make different kinds of declines if you have more voxels and more qubits. Yeah.
And if you want to survive, basically.
Yes.
Yeah. Okay, next question.
But I also think like maybe this was in another version, because on the left side it does this.
The left side looks much better.
Yeah.
Jan?
So it's work on progress.
Absolutely, yeah.
Yeah. So thanks a lot for the presentation. And I especially liked your discussion of quantum advantage, yeah, which is very important, because if it does not provide an advantage at some point in time, we would stop doing that, right, quantum. So that is actually my first question. How do you define quantum advantage? Or what could be the advantage?
Yeah, I think we have two different approaches to talk about it. The first thing was with RWTH, which is basically doing the same thing as the D-Wave quantum computer. So when you have an advantage there, that would be nice, first of all. But the more important thing is if you can actually compete with classical algorithms, like the first one we presented. And that difference is even bigger than the one with the RWTH.
And I think here in this case we were referring to the current state. So like what can we do now? We know that the main promise and the great idea of quantum is that it scales much better than the classical computers does. But here in this moment we decided that the classical computers still outperform the available quantum hardware, which is why we say that there is no quantum advantage to using it at the moment.
Mm-hmm. And so I think there are different views of, or there can be different kinds of advantages. Yeah, so one could be that you can handle larger problems, you can handle them faster, get a more accurate solution, or maybe get a similar solution but much more energy efficiently, yeah, using less resources. And that is very different for different problems. Yeah, what kind of advantage you can achieve. And okay, so I mean the status is no quantum advantage there. And is that a surprise?
No.
Okay.
It's just that we try to, so for us it was also our journey into the quantum world, and we just wanted to see the state of the quantum computers at the moment, and this is what we basically experienced as coming from the classical world, that there is the potential, like quantum has a lot of potential, but given the current state and the challenge that we were faced with, we'd rather choose classical at the moment rather than going the quantum route, or using the hybrid approach that we presented.
You wanted to add something?
Just a small thing. I think it's sometimes really difficult to map a problem for the D-Wave into Cubo, and for some problems it's easier than for others. So I think there could be a quantum advantage for some problems, but not for others.
And better algorithms than ours.
Okay, more questions?
Hi, I would continue with this topic. So I sincerely hope that you are wrong, because if you're calculating by your method the 8 years up to 1 million qubit, I hope we are going to get that there faster, and especially big companies like IBM, Rigetti, and Google might contribute to that. But I also hope that there will be some, let's say, side surprises from neutral atoms and others who will get there even faster. So that's one thing. And the second one, if you can explain how did you get this idea to use Moore's law for the quantum computing? Because I thought the whole essence is to overcome this idea. Just out of curiosity. Thank you.
So I think regarding the first question, I mean, there is obviously scaling problems with our algorithm. I think there are more efficient solutions that also require less qubits that could then probably be implemented even earlier than this. And I think at the moment, the Moore's law was the most applicable one for us coming from a classical world. And I'm not aware of any like scaling law for the quantum world yet.
Yes, and I also think I want to add to the first question. I think like some problems are really easy to map on quantum annealing, and some other problems are not that easy. For instance, like the traveling salesperson problem, I think that's it's much easier to map on the quantum annealer. And I think for this problem, it was quite hard to find a solution which is really good scalable, at least in my opinion.
Yes, and just to add to that quickly, also regarding the first part, actually, I think there's, as you mentioned, there's a lot of different platforms also that are possible in principle, and it's, at least to me, honestly, not very clear at the moment which will be the final platform that actually will be useful in any sense. And it might be that some kind of superconducting qubits will be very useful. It might still be that neutral atoms will be very useful, or trapped ions or whatever. And we'll have to see about that. And it's also very possible that they all scale very, very differently depending on also where they are in, at which stage of development basically are at.
Me too. I hope you're wrong.
Me too, but...
Awesome, thank you so much.
Thanks.
Yeah.
Can you go into more detail of your idea of space reduction, especially clustering?
About how we want to do it. How we want to do the clustering. For instance, you could just pick if you are optimizing a single airplane, then you know where it will be located roughly at a certain time spot, and then you will see if an airplane is getting close to each other, and then you have to put both of them in the same optimization algorithm. But if there's another airplane which is not even coming close to it, or a set of other airplanes which are not coming close to that one, then you can just solve that problem separately.
And this is what the hybrid solution would give us, where we initially have a very basic optimized path, which might not be perfect, but at least it gives us a rough direction on where the plane wants to go, probably. And then we can pick out sets of airplanes that we then use, that we then optimize in a separate way. And this means that we need less qubits or resources to do the calculations, because it's really expensive to check for the collisions between all of the possible routes.
Any more questions? Doesn't seem like it. So I have a question.
Please.
A nice one. So now that you journeyed into the quantum world from the classical world for this challenge, will you stay in the quantum world or will you leave again?
So I think for me, I will be definitely an eager observer. At the moment, I don't really have a day-to-day interaction with quantum yet, so there is no real way for me to get into it. But I think it has, as I already mentioned a couple of times, great potential, and I'm really interested to see where it overtakes the classical computing and where we will use it in the future also to substitute it.
I think it's definitely something which I will follow and look where the journey is going to. So I think it's a really interesting topic also for researchers and yeah.
Yeah, I'm very much more on the research side of this, and on actually I'm a little bit more coming from neutral atoms perspective, basically, and also building these kinds of machines and on developing algorithms to be a bit more on background here. So, and I'll definitely still be in that field for at least a little while.
Yeah. So we have to. It's 1 year until you look for a job, right? So, so Jan has to hurry up a little bit even more, so that in a year you will choose the quantum career path. Okay. And time is up. So thank you again.
Yeah,
thank you.
And yeah. And for our final pitch of the day, we welcome again an individual, not Felix. We chose the running order randomly, so there's just coincidence that you're the last pitch of the day. And very happy that you are here as well, and you can introduce yourself basically. So give a round of applause and have a great pitch.
Okay, so hi everyone. I'm Felix, and I'm very happy to be presenting my solution to the quantum climate challenge today. So just as a quick introduction to myself, so you can get a better understanding of where I was coming from with my approach. I'm a physics student at the University of Copenhagen in Denmark, and my main expertise are in 3 areas, mainly unsupervised machine learning in condensed matter physics, performance optimization of very different quantum algorithms, and of course also trying to solve real-world problems using quantum algorithms, which was also my motivation to participate in this challenge. So, for the last time today, I will give a very quick introduction to the problem that we all had to solve in the challenge. So the general task was that we had a set of flights distributed over Europe, and a climate model which we could use to compute climate cost for a given flight. Using an aviation model that specifies the fuel consumption and the velocity at different altitudes, we were able to find trajectories that try to optimize this target parameter delta t right here, which is a function of fuel consumption and the path flown of all the trajectories in our optimization. Another important aspect to consider during this challenge was flight safety, because of course, if you optimize or find these climate optimal trajectories, you always have to ensure that they're actually physically feasible to fly due to the limited maneuverability of the planes, and also to ensure that, well, planes don't crash into each other. I'll now continue with the formulation of my problem. Initially, we were given access to a 7-qubit device, which is, of course, super nice, but you have to be really conscious on how you formulate the problem in order to actually get some meaningful results for the trajectories that you're trying to optimize. So my approach to reduce the number of decision variables was to split the problem into optimizing a single trajectory first, and then to deconflict the flight plan afterwards. For the single trajectory optimization problem, I introduced the same discretization as in the climate model, which basically means that in my model, planes fly from climate voxel center to voxel center. And the simplified target parameters then this delta ti, which is now a function of the fuel consumption and path of a single plane, basically. For finding deconflicting conflict between two planes, I came up with a solution to modify the trajectory of one of the conflicting planes by plus or minus 20 flight levels, which we can model as a binary event. And then I formulated this problem as a quadratic unconstrained binary optimization problem, as we heard today before, which has this cost function Q right there, which consists of two parts, namely a climate cost function of the changed trajectory and a penalty that penalizes any new conflicts that would be introduced by this change, or if the changed trajectory would violate any other flight safety rules, for instance, go outside of the aviation model. And the optimal solution to this, to the number of conflicts that we have, is then this bit string right here that minimizes this cost function Q. I'll now try to explain some of the methods that are used to solve this challenge, and some of the slides are a bit more technical, but I don't expect you to read all the text. That was for the discussion afterwards. So that's it. One of the algorithms that I'm using is Grover's algorithm, which is, I guess, one of the most well-known quantum routines out there, where the basic idea is that you have an unstructured list, and you want to identify an item with a unique property. And the interesting aspect about Grover's algorithm is now that it does that in with a quadratic speedup compared to the best classical algorithms, because Grover's algorithm only has a runtime complexity of O of square root of n, which is faster than the O of n that the classical algorithm needs. One main caveat of this Grover's algorithm is that you actually need to know the property of the item that you are looking for beforehand. In the example of the trajectories, this would mean that we would need to know the minimal climate cost before we construct the problem, which of course doesn't make sense, because then we wouldn't need this whole quantum search algorithm. So I'm using a slight variation of the Grover's search algorithm, which exactly doesn't need to know the minimal cost that we're looking for beforehand, but this algorithm here iteratively updates the marked item and iteratively updates the number of Grover iterations to reach or find the item with the lowest cost, while still maintaining this runtime complexity of O of square root of n. yeah, because this was all a bit technical, I'm also going to give a very quick rundown of how I actually use this to compute a climate optimal trajectory. So, for a given flight I, we have a set of starting coordinates, x, y, z, and t, and a set of final coordinates, x and y. What I'm doing here is to fix a final altitude to, for instance, 100 flight level, and to then generate a set of trajectories that connect start and end point. Then I'm using my quantum search algorithm to find the best trajectory with that final altitude. And then I repeat this process for all possible final altitudes to give me an overall best trajectory in the end, which in this case is this trajectory in yellow here, which is not that nicely visible. Yeah, so now on to the second part of my work, namely resolving conflicts, utilizing filtering variational quantum eigensolvers. So, as I mentioned in the beginning, this problem of trying to deconflict a certain set of flights was formulated as a QUBO problem, and we now want to solve this QUBO problem on a quantum device. A convenient fact that we can use is that QUBO models and classical Ising models are computationally equivalent, which means that with some algebraic modification, we can express this QUBO Hamiltonian as a classical Ising Hamiltonian. Then using a simple coordinate transformation from binary variables to spin variables and expressing our problem in terms of Pauli Z operators, we can now solve this problem using a quantum computer, as the optimal set of detours is now encoded in the ground state of the Hamiltonian. Now we have a couple of different routes to try to find that ground state of the Ising model, and as we are dealing with near-term intermediate scale quantum devices, I chose to use variational quantum algorithms, where the basic idea is that you have some parameterized quantum state that generates a trial state, which you can use to compute an energy expectation value of the Ising Hamiltonian, and using the variational principle, you can then tune the parameters to find a state that is the ground state or near the ground state, which means we transformed our optimization problem to this here, which is basically finding a set of variational parameters that minimize the energy expectation. The variational quantum algorithm of my choice that I'm using uses this concept called, or borrows from this concept called imaginary time evolution, which is a simple but profound concept in physics, which we can understand if we look at the diagrams on the right-hand side here. So suppose you have some wave function of which you want to sample the ground state with high probability. The ground state is this state marked in green here. Of course, in this basic implementation here, this isn't easily possible to do. So the idea of imaginary time evolution is now to basically introduce a change of variables that introduce a prefactor onto the energy eigenvalues of each state. And the interesting thing is that this prefactor is inversely proportional to the eigenenergy of the states, which in plain English basically means that the higher the energy of your state is, the stronger it gets compressed. And if you have a state with a low energy, it doesn't get compressed as much. And with that, you're able to kind of project out the ground state out of your superposition of other states. And this is nice and interesting concept, but there's one problem, namely that this imaginary time evolution is a non-unitary operation, which means you cannot actually implement it on real quantum hardware, because quantum hardware uses unitary gates. To solve this problem, I'm using the so-called filtering variational quantum eigensolver, which basically asks the question of what's the best way to approximate the action of a non-unitary operator with a set of unitary gates, which we can see here. Does this work? Yeah, this cost function C of theta. So at every optimization step, we generate a trial state that should be as close as possible to a quantum state on which a filtering operator was applied. And a filtering operator is basically just the extended version of the imaginary time operator. And yeah, with each optimization step, we are getting closer and closer to this image here, basically. And then in the end, after a certain number of iterations, you can sample the circuit and you get the ground state with large probability. I can also show a couple of results that I computed with these different methods. This is just an excerpt of a couple of trajectories that I computed with the quantum search algorithm, where we can kind of identify a general optimization strategy, namely that the flights after the optimization starts, they quickly change their altitude to around or above 300 flight levels, which can be explained as there is a better balance between fuel usage and velocity of the planes. We can also try to compare the trajectories that I computed with some classical optimization, and for that I chose a very simple classical optimization. This I called it the shortest path optimization, which basically are the trajectories that just fly a straight line from the starting point. And we see that we can actually get some nice improvements compared to the classical optimization. Namely, we get a reduction of the climate impact of around 23%, and surprisingly, also 11% improvement in flight time, and also slight improvement on cost effect. And I was actually pretty surprised when I first thought that, but I would attribute it to the fact that most of the planes take a trajectory that looks like this here, which means they climb to above 300 flight levels, which means they can actually have they can fly faster. They have a larger true airspeed, which means they reach their destination faster. So that would be the explanation for this surprising improvement. This is an example of a conflict that I resolved, where we have these two conflicting flight curves that, the conflict was resolved by a detour of plus 20 flight levels. And I also did that, basically the same process, but optimizing 16 conflicts simultaneously. And an excerpt of these 16 conflicts are shown here in this table, where we have the flight index, the index at what point of the trajectory the conflict is happening, and then, I guess the detour that was found. And as we can see, we're able to kind of resolve the conflicts with only very minimal change to the overall computed climate value. And no new conflicts were created in the process, which is also good. So that was my presentation. I look forward to the questions.
Thank you very much. And then for the last time, floor is open for questions. Who wants to start?
Now I have to give me a second.
Yeah, sure.
At the very beginning, you shown how you generated multiple paths. No, it was about calculating paths with different. Yeah, exactly this.
Yeah.
I didn't understood how you combine multiple solutions to a single one.
Okay. So I apply this quantum search algorithm 2 times in this process. First, I generate a certain number of trajectories from that all end in the same final altitude, and use the quantum search algorithm to find the best trajectory out of that set. And then I repeat this process for all final altitudes, and then apply the quantum search algorithm on the basically best outcomes so far for all final trajectories. And that gives me a pretty good solution overall. Does that make sense?
Does it require all those trajectories to intersect on the 2D dimension? Or no? Okay. We have to talk afterwards.
Yeah, sure.
And the next question would be, you've compared your final solutions, comparison, how the time and climate costs were improved.
Yeah.
By shortest path, you mean the direct connection between start and end?
Yes.
Is it vertically already optimized, or is it just on an arbitrary level?
It's on the level that the flight starts at, because we were already given a starting altitude. So just basically taking the starting altitude and then a straight path to the final destination.
Okay, thanks.
So, hi. In many cases, it is possible to use QAOA instead of VQE. Is that also possible here, or because of the filtering VQE not?
Yeah, exactly. These filtering VQEs only work with VQEs.
Okay.
So yeah, that is like a specific concept that wouldn't work for QAOAs.
Okay. And the implementation, have you published that? Is that available?
Yes.
Okay.
Yeah.
And, so short answer, but yeah, that's good. And did you use also real hardware, or did you run on the simulator for the results?
Partially. I ran the this quantum search algorithm on real hardware, but to be fair, I wasn't able to implement these filtering VQEs on actual hardware. I only ran simulations for that.
Okay. And you did not try on real hardware, or were there any issues because of error and noise that it did not converge or so?
I tried, but wasn't entirely sure how to manage to get good results. Yeah.
Okay, more questions?
Exactly on this graph here, I'm a little bit surprised. You said that the reference you're comparing that to is the climate optimization with the classical tool, right?
I mean, the classical case that I'm comparing this to is basically a non-optimization case. It's just simply a straight line. So, yeah.
Okay. I'm just thinking about the time effect and the cost effect.
Yeah, sure.
The time effect means that if you have a sort of a detour, then you have to fly faster. Then detour plus faster probably means you use more fuel and more time. Then I'm a little bit surprised that the cost effect is going down.
I would attribute it to the fact that the velocities at higher altitudes are faster, and therefore we can get a reduction in overall flight time just by the fact that the planes fly faster. I think that was kind of my resolution to this question, which I also had because I was surprised to see this.
So the base case, the reference is at a certain altitude, which is probably not optimal to.
Oh yeah, exactly.
Okay, good, thanks.
Okay, are there any more questions? Otherwise, I have a question again. So, so you said you're currently doing your master studies, right? So do you already know what comes next? Or are you looking for a job? Or what's your situation?
I'll start my PhD next year. So.
Do you already know where and about what? Or can you talk about it?
Yeah, sure. I mean, if everything works out, I'll be going to the University of Leiden in the Netherlands doing condensed matter physics-related stuff. Yeah.
Cool, yeah. Good choice. Yeah, any other questions? Doesn't seem to be the case. So then I would say yes. Big round of applause again. Thank you very much, Felix. And then now it's time for our jury to go to the discussion room and, well, put their heads together and decide who will get which of these nice prizes to take home with. Yeah. And for everybody else, please discuss and meet the teams at the tables. Each team has a table where they will be at and are happy to answer questions. And I think also Karen will be at one of the tables. Yes? Yeah, perfect. So you can also mingle with him. All right, thanks. Ah, yeah, and we will be back at 5:45 for the winner announcement. No, yeah, we will be very strict. We will be as strict with the jury on timing as we were in the pitches. So 5:45 it is, sharply. So for the last time today, attention please. The moment of truth has come. We had quite an intensive discussion. So, well, obviously we have 5 prizes, and everybody who was invited to pitch today already is a winner. So first of all, please a big round of applause for everyone again. And also, so the vote wasn't unanimous, so there as it always is. We have reached a verdict, but nevertheless, even if you're in the lower ranks, please be assured that your solutions were really tremendous, and what you achieved in just 6 weeks was, yeah, we are all very, very impressed with every solution that was handed in. Okay, but with no further ado, for the presentation of the winner of the 5th prize, yes, Oliver, I have a microphone for you. Yeah, so Oliver, please take the trophy for the 5th prize, and I leave it to you to announce who it is.
I can only say that indeed everybody is a winner who was here for a pitch today. And I was very impressed from one participant because he solved it alone, and he solved it both steps with quantum algorithms. So, Julian, please come to me, and really, you impressed me a lot.
Thank you very much. Thank you very much. And this comes, of course, with 1,000 euros, so congratulations. Okay, so next up, yeah, perfect, Andrea, 4th place. Please come to me, take the mic, and please announce the 4th place winner.
So as Barbara said already, all you concepts were tremendous for us, and I would like to ask the Friends of Pluto on stage to get the 4th prize. I was especially amazed about your challenge on what can quantum computing do today. And I believe that IBM really got the challenge now to make the advantage of quantum computing. Thank you very much. Great.
Yes, and that, of course, also comes with 1,000 euros. And now for the top 3, we also not only have the cash prize, but we also have some prizes from Terra Quantum and from Anacor. So. Do you want to come on stage and explain a bit of what your prize is about? Sure. Yes, the mic over there.
Thank you. Good afternoon, or good evening, I should rather say. From us at Anacor, again, also from our side, congratulations to everybody. Thank you for the invitation. Thank you for the organization. It was really a special afternoon for us, and we're particularly proud to be able to also donate one of the prizes. We are Anacor as a new brand of Stone One, and as part of a research project funded by the German government, we are developing the Planck platform. Some of you may have heard of it. With some of you, we have already been in contact and have been talking about all the research that we've been doing. Planck is a platform that enables quantum developers such as yourselves to take the code that you have written particularly for this challenge, to containerize it and to push it to actual paying clients. So with the Planck platform, what we want to enable is quantum developers to actually monetize their experience that will be needed to solve problems such as climate challenge, and also in all the other industrial domains that we can think of today and that we can't even yet think of today. And we are very happy to offer the best 3 teams an access to the actually currently running closed beta. So you will be able to work with our development team to see how to upload your solution on the platform, how to potentially give it to actual airlines, and how to figure out how to continue working on that solution that you have built up to this point. And I think that's the very short synopsis. We're here with 2 additional colleagues, so if you have further questions about the research project, about us, and about the platform, we're more than happy to welcome that, and we're happy to be here today. And we are now very curious about the next 3 spots on the list.
Yeah, you have to wait a little bit longer, I think, because Karen, do you want to say a couple of words about the Terra Quantum prize? Yeah, maybe also Volker, I'm sorry, but not yet, but next.
Great, I think every team here should be so proud of themselves for what you guys have done, really, yeah. And so for the winner, what we're going to offer you is 48 hours on our hybrid quantum cloud system, QMware. Okay, because I think a lot of the algorithms that you guys have could do really well through deploying it on QMware. But because I see there's a gap in actually understanding how you could take advantage of hybrid, that is bringing a simulator, a native QPU, and hybridization on the quantum classical element on the software level together, we're also going to offer you 1 hour of a quantum expert, a hybrid expert, and our quantum trainer to help you hybridize your algorithm. So hopefully you can have a hybridized algorithm that's executed on the QMware cloud, and more time to experiment and see the performance of it there. So that's for the winner. Cool.
Thanks. And now, Volker, please take the trophy with you and the mic.
Yes, we had a hard fight for the jury. I'm happy to survive, and it's really only small differences between all the winners. For me, they're really all winners. We had great solutions, and as I said, the difference is small. So I'm happy now to announce the 3rd prize. The 3rd prize goes to, and I'm especially happy to give the prize to them, because in the coffee break we already had a discussion and brought the ideas forward, looking at the probability distributions and the climate functions. And the winner of the 3rd prize goes to Lufthansa Industries. Congratulations. Thank you.
Okay, and now on to the 2nd place. And yes, Anton, perfect, already coming on stage. So I step aside.
Yes, I was really impressed what small teams can achieve in such a short time. And especially I was very impressed what one person can achieve in that time. And therefore, Felix, I would like to ask you to the stage.
Yeah, we have time for photos later, sorry, but yeah. Okay, so, well, 1st place, Jan,
okay.
honor is yours.
That is now not a surprise. Team Quantimize, please come on stage. And yeah, you had a very good introduction. You really reminded us what this is about. It is about climate, sustainability, and our future on planet Earth, right? The solution that you have produced, the 2D solution that runs on both on an annealer and on a gate-based system, which is very good. The 3D solution, you assume that we have Qubits. I think that needs some research, but some of you study quantum technology, so that is something that you can work on, obviously. And to one of my questions, I think you asked me then back if I know a bit about quantum hardware from IBM. And yes, I can reveal that I'm from IBM. Yeah.
I got to know that, yeah.
And Okay, so I wish you all the best and good luck on your quantum journey, and I hope we will hear more from you in the future.
Thank you very much.
Congratulations. Das ist ganz wichtig.
Okay, and we actually have another announcement, a special prize that Andrea came up with after hearing the solutions.
Thank you. Yeah. So first of all, I've learned today that quantum computing can release noise, and noise is one of the errors you get if you really try to do it. And then I've seen people that say they are noisy, but they are not necessarily been noisy. Julian, would you like to come back on stage, please, for 1 second? One of the discussions we had is how much is it quantum computing challenge and how much is it climate challenge? And we really liked your approach to say we should make it simple, and you said you like simple solutions. We at MTU, we would need simple solutions, and we have an innovation management week beginning of July where we actually have a quantum computing pitch, and we would like to invite you for MTU, join us for that week and basically approach a bit the aviation part of quantum computing. Yeah. You're welcome.
Okay, so that is kind of the end of the official part. But before you all leave, so first of all the winners, we want to take pictures with all of you afterwards, so please don't run away just yet. And then I would like to say thank yous, first to the jury. So if the jury members could please come up on stage, because of course we also have stuff for you. Yes. Oliver, thank you so much for being part of this. Anton. Thanks to you as well. Volker, you get, well, actually I give you 2. You have for your colleagues back home. But you have to share two with the 3 of you. That's, yeah. Jan, 1 for you. And last but not least, thank you very much for being here.
Thank you.
Yeah. And then also, of course, thanks to everybody who made this event possible today. So the KI Park team, Veronika, Florian, thank you very much for having us. And then the Deloitte team, so Quantum.Link, Niklas, Markus, Henrike, Tobias, Zineb, thank you so much for being such an amazing team. And I would actually like you, Henrike, to come up on stage as well, because Henrike is actually Henrike's last day today at Quantum.Link, which is very sad. So she came to join us on her trainee journey and was supposed to stay for 4 months, but then after the 4 months, she actually decided to keep working on this climate challenge with us for a bit longer. And so thank you so much. Thank you. It was a great pleasure and honor to work with you. And you know that you always have, you know, if you want to come back in the future to Quantum.Link, there's always a spot open for you. Special thanks to you, and you also highly deserve one of those nice bottles.
Yeah. So maybe, well, thank you, Barbara, for this really kind gift. And but I also want to say thank you to you, because without you, this challenge wouldn't have happened. You have put so much work in it, so much time and heart, and also stress maybe, and to make this happen, to get us all here, to get all the participants, and also the jury, the KI Park, everybody, to get everybody on board. So thank you very much. I think that was fantastic.
Yeah.
Great.
Okay, with that, time to start drinking. Networking. Yeah.